or axioms which replace theorems. So instead of having a proper definition upon which theorems are then created and proven, we decided to not define what the word set precisely means. And so the various facts about sets, which would ordinarily be theorems if this was any other mathematical subject, are replaced with rules, axioms, things that you believe in because you're told to believe them, or perhaps because you believe that they correspond to your intuition about what ought to be true, assuming that your intuition actually reflects something valid. What's really happened, although people don't want to say it this way, but this is really close to the truth, is that philosophy has come to the rescue of modern mathematical foundations. Mathematicians themselves were not able to create a proper framework for set theory. They tried, but it didn't work. It failed in a very embarrassing and flamboyant way, in fact. And then the philosophers were kind of recruited. They were brought in and they created this essentially philosophical framework, really is what it is, which is now the underpinnings not of just set theory, but remarkably, supposedly all of pure mathematics. Absolutely incredible state of affairs, people. Absolutely incredible. And future generations are going to shake their heads in disbelief at what we've gotten up to, and what we've allowed to pass as a proper foundation for a subject. So why did modern set theory go down this road? Why this retreat from proper definitions? I'm going to be explaining the history of this in some detail this year. We're going to have a very close look at this whole story. We're going to look at the axioms very precisely and carefully and critically, and we're going to unravel the whole logical knot. So it's not just the definition of sets themselves, which are missing from the current theory, but pretty well all the other adjacent terms are also sort of imposed without proper definitions, such as, for example, element, union, power set, intersection. So none of these terms are pinned down precisely. And you might say, well, why did people do this? This is clearly not a very desirable state of affairs, so what motivated mathematicians to accept this? And the simple reason is the following, is that if you accept Cantor's definition, so here's Cantor's original definition of what a set is. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. So if you are going to accept this as a definition of set, then you have serious problems, because this is just not precise enough. What are objects of our perception or of our thought? And you've already seen me give various lists of suitably ambiguous kinds of sets, and do they really deserve to be called sets, or don't they? But the fundamental problem is already at this level here, which is really sort of at the level of a 10-year-old objection. If you're going to just allow yourself to think up sets, as I'm thinking of certain things, the set of all fish called Fred, okay, it's a set because I'm thinking of it. The set of all happy thoughts, yes, that's a set because it's something I'm thinking about. So if we play this game, then even primary school children can easily come up with ever more and more outlandish sets. And eventually some kids will say, hey, I've got a set that will beat everybody else's set. How about the set of all sets? Okay, it's not particularly brilliant insights to suggest that we should consider this, but we can consider sets of anything, then how about the set of all sets? And this is really the fundamental core problem. It's the fact that you can create a phrase like this to create an object which is almost self-evidently contradictory, or at least highly dubious. Here's the set U. And it's got every single possible set you could possibly imagine. The set of all fish called Fred is in there. The set of all happy thoughts is in there. It just contains all possible sets, including you itself. You as a set. That's what belongs to the set of all sets. Okay, but that means that inside this U, if you look more carefully, there's another U. Inside this copy of U. And inside that, there's another copy of U. And in fact, this U is sitting inside some bigger thing, which is also a U. So this is infinite digress in both directions. And I think most reasonable people would say, guys, you have crossed the line into nonsense. It doesn't work. This is silly. You're obviously going to be faced with self-referential problems here. Okay. So people generally think that it's because of Richard Russell's paradox that's set theory classified. In fact, it's really just the ambiguity in the definition of Cantor. Even at this level here, which is, I think, essentially like a 10-year-old kind of idea, you can see that this is not going to work. But there's something seriously logically problematic with trying to conjure up set theory when you're only going to have something that's so vague like this as your fundamental definition. Okay, so I realize that people are going to kick and scream about this. Analysts are going to be loath to accept this because they all know that modern analysis is built on the foundation of set theory. That's the ultimate justification for our model of the continuum as real numbers. And without real numbers, most of modern analysis is very seriously weakened. So there's going to be strong resistance to actually even addressing this entire issue. Most analysts would just rather not think about the problems with set theory. Like most mathematicians prefer not to think about the problems. But the problems are there, they're very serious, and there is a better way. So we are going to point to a better way. But there's a lot more to be said about that, and I will be talking at length about this entire issue. So now let's go to cardinal and ordinal numbers, which are part of this modern set theory, which we don't believe in. We don't believe in cardinal and ordinal numbers, so neither of these are proper mathematical theories, in my view. But nevertheless, let's have a look at the standard story of ordinals in particular. So here's a relatively simple quick introduction to ordinals, sometimes also called the theory of well-ordered sets. Okay, so I'm going to just show you the standard hierarchy of ordinals. So we start with the empty set. So everything is a set in this theory. That's maybe important to say. So everything we're going to consider from now on is going to be a set regarding ordinals. And the simplest possible set is the empty set. Fair enough. And that's going to be given a name. We're going to call that 0. That's going to be our representation of 0. And that's certainly not unreasonable. I perfectly buy that. And then we have to build up numbers from that. The idea is to build up numbers by just looking at sets of sets, positive sets, and so on. So the simplest set that we can build from the empty set is a single set whose sole element is the empty set. So it's a set consisting of 0. And Levy knows that the set consisting of 0, which is this one here, can also be written as O union this set. It's always the empty set, and the empty set union is this thing here. All right, now the number 2 is defined to be 1 union the set 1. So it's a new set, which is a union of 2 existing sets. The first set is the set, which is 1, and then the next set is the set which contains 1. So here's this union. So it's a big set, and it's got one element there, which is the element from 1, and then the other element here is actually this entire set. So this is the union of the set 1 and the set consisting of 1 as a sole element. Please check to see if you agree with that. And then 3 is defined as 2 union the set 2. So 2 is the set, namely the set right here, and then we take the union of that set with the set consisting of just the element 2. All right, and here you see all of this put together. So we're taking the union of this, which is that part there, together with the set 2. And there's the set 2. Okay, notice that I'm reverting to standard notation here for sets. So I'm using commas because this is traditional treatment. So a standard set here is we'll look at this and say, yes, this is the usual way that we build up natural numbers from sets. Essentially from just the empty sets and constructions of sets. So all of these sets that we've constructed so far, 0, 1, 2, 3, and so on, they are all called ordinals. And the pattern that we've used to go from 0 to 1, and then from 1 to 2, from 2 to 3, and so on, can be generalized to define the successor of any ordinal. So if alpha is a ordinal, then its successor alpha prime, which we can also write as alpha plus 1, is defined by, well, here's that rule that we've seen. Alpha prime is the union of the ordinal alpha together with the set consisting of one element, that element being alpha. So this is a set, that's a set, we're taking the union of those to create another ordinal, which is the successor of whatever ordinal alpha we started with. Okay, so this is actually been a perfectly logical, yet complicated way of constructing the natural numbers using only finite set theory. I have no objections with this as a framework for natural numbers. I think it's not the most efficient way. I think that it's definitely constrained by having this idea that sets are the right data structures to use. We know that there are these other data structures that are around, namely lists and ordered sets, and particular multi-sets, in addition to sets. And having these 4 different types of data structures around provides us with more flexibility. So we are going to, in fact, be looking at something like this, but we're going to be doing it in a different way because we're not constrained to just stick with sets. But if you were constrained to stick with sets, then this would be a perfectly natural, in fact, reasonable and somewhat clever way of creating natural numbers from set theory. And this is, I think, basically attributed to John von Neumann, a brilliant American mathematician of the 20th century. Okay, so we have now a way of constructing natural numbers. So 0, 0, 1, 2, 3. So they're all sets. They're all things we call ordinals. And, okay, we have a sort of inductive way of getting from one to the next one. So far, so good. All right, so now the dubious part of the construction of ordinals. The idea of taking limits of ordinals. So suppose we have alpha 1, alpha 2, alpha 3, and so on, a sequence of ordinals. So we have some rule that generates what we consider a nice sequence of ordinals, or suitable sequence. Okay. Then their limit is defined to be their union. Alpha 1, union alpha 2, union alpha 3, union alpha 4, and so on. We call that alpha infinity. So this is a way of starting with a sequence of ordinals and taking some limits of that sequence. And it's analogous to the kind of limit that we get the set 0, comma 1, comma 2, comma 3, and so on. So what we're getting when we take the union of all of these things is an infinite set. And here's where the problem really arises. The problem is that if there's an infinite number of elements in your sequence, then you're asking to take the union of those infinite number sets, and that's simply something that we cannot do. That's the basic problem. You cannot do that. So you can take the union between two sets. And then you repeat that, you can take the union of three sets. Repeat that, you can take the union of four sets. Fine. But you cannot take the union of an infinite number set. It's not actually even defined. So I hope that we can appreciate the difficulties here, because these three little dots, which represent the union of all the other natural numbers, we know that this is hugely problematic, because we have now some experience with numbers which are considerably bigger than just 1, 2, 3. We know that this seemingly simple-minded pattern, one number followed by the next, followed by the next, doesn't in fact really represent what's going on here. Along the way here are things like Z, and then Z prime, and then like that number 3 star n4 that we started to write down the expression for. And in between 0, 1, 2, 3 and Z prime and this big number are untold numbers which cannot be written down in our universe because they are too big. These are numbers whose existence is problematic. And that's not to speak of at all the numbers supposedly which are beyond even that biggest number that we contemplated. And even numbers which are so big that you cannot write down any expression for them at all in the universe. So eventually the universe is so big, eventually you just run out of possible numbers that you can write down in the universe. It's only a finite number. You don't know how many, but there's a number bound. Okay? But we're pretending that none of that applies here, that we're just closing our eyes to the reality of mathematics as it really is, and pretending that this little sequence keeps on going in a simple-minded fashion, and that therefore we have all of the natural numbers in one big set, and that's going to be a new object, which we're going to call the ordinal omega. And that's the heart of the problem right there. The heart of the problem is already omega. This object does not make sense. Simple as that. But the set theorists pretend that it does, because it sort of coincides with Cantor's vague prescription. Well, we can think about all the natural numbers, and because we can think about them, we can put them all in a box. Okay, so now the idea is that using successors and limits, set theorists now construct a hierarchy of ordinals. So this is the beginning, and now by combining these two operations, we can build higher bigger ordinals, which, somewhat surprisingly, has a remarkable similarity to our hierarchy of arithmetical operations, the star lambdas. Even though these are quite different objects, and even though this is, in my view, highly dubious logically, nevertheless, there's a very close parallel to what's going on. So, for example, once we have omega, we can talk about omega plus 1, which is the successor of omega. And by definition, that's the set omega union the set omega. Okay, well, what does that look like? Well, here is the union. So there's omega, and there's a set containing omega, and we take the union. Or we can sometimes write it like this. So here's sequence 0, 1, 2, dot, representing all the natural numbers there. And then there's a little colon with an omega afterwards, representing the fact that after you put in all the natural numbers, finish that task, close off the little sequence with a little semicolon, and then you add omega itself. Omega and then the same kind of thing. Alright, so that's the successor of omega. And then we can take omega plus 2, which is the successor of omega plus 1, which is omega plus 1 being set omega plus 1. And we get something that looks like this. And we can carry on, and then once we have these guys here, then there's a limit procedure that we can take, and then we can take the union, and we'll get 2 omega, which looks like this, and it has a infinite sequence of the sort of first level ordinals, just natural numbers, and then these sort of second level numbers, omega plus 1, omega plus 2, etc. And there's another infinite sequence of those. Okay, so then the story continues, and it's very parallel to the kind of picture that we were drawing, except that the crucial role of limit has changed dramatically. The objects that we're considering are quite different. We're talking about infinite sets here, whereas we were talking about operations between natural numbers. Right? And here, this limiting operation involves doing a limited number of things. For us, that's not the case. For us, the limiting operation involves writing down a formula that allows us to compute very concretely and specifically, if in a very complicated way, the product of two natural numbers. So the limit of omega to omega 3, omega so on, is omega squared, and then the limit of omega squared, omega cubed is omega to the omega, and we get a hierarchy of ordinals this way. In fact, the hierarchy extends much further depending on various sort of higher discussions that we call it. So we see that there's a correspondence between what we're calling n and what the modern set theorists call omega. So even though they are very different, the contexts are very different, still there's a correspondence between these two kinds of ladders, suggesting that the ladder itself gives us some kind of independent interest and has a life of its own. Perhaps independent of ordinals, and maybe independent of operations as well. So that's a very case. It's a very interesting object. And this time I think we want to explore a little bit more of it. So please try to get your head around what we've done today with regard to these higher arithmetic operations. And we're going to push further into to see how these different levels of limits start playing an important role in determining what kinds of sequences are suitable for taking further limits. It becomes quite interesting and sort of self-referential in an interesting way as well. So I hope you're learning for that. I'm Noah Robert. Thanks for listening. Okay, I'm Nolan Robert. Today we're going to have a further look at this successor limit hierarchy of mathematical operations and connect it to a rather traditional area of modern set theory having to do with ordinals. Now, I'm not a big fan of modern set theory, to be honest, and I don't think the theory of ordinals really works in its current form. But nevertheless, it's still going to be interesting for us to compare this ladder that we're creating with a similar kind of ladder that appears in this self-dubious theory of ordinals. So the setup is that we're looking at arithmetical operations on natural numbers, and we have basically two cool ways of creating bigger operations from one is the idea of a successor, and the other is the idea of a limit. So a successor, if we have some operations, say circle cross, it's an actual arithmetical operation on natural numbers. So if we have two natural numbers, m and k, then m circle cross k is another natural number. Then we can define its successor, circle cross prime, inductively this way. We define how we multiply m by 1, m, and then we define how we multiply m by k plus 1 in terms of how we multiply m by k. And here is where the original circle cross operation comes in. Okay, the other idea is that of a limit. So if we have some suitable sequence of operations, circle cross 1, circle cross 2, circle cross 3, and so on. So by that we mean we put a figure on a certain pattern that we want to identify. We have a very clear idea of how to generate all of these. So we have a uniform way of getting all these elements in the sequence. Then we can create something that we could call the limit operation, which is sort of a limit of this sequence of mathematical operations, and it is also an operation. Now here's its definition. So m circle cross infinity k is defined in terms of one of these, in fact, in terms of the k one. So it's m circle cross k, k. So we look at the second entry of the two numbers that we have here, the k, and then we go down our sequence, find the k one, and we use that to multiply m and k. So that's the definition of this thing here. So this is especially powerful when k is big. As k gets big, then we're using bigger and bigger, typically, operations here to generate bigger and bigger numbers. Now there's a little bit of an art form here because we'll see that it's not entirely obvious what a suitable sequence means here. Okay, so at this stage, this is just kind of an art form, and I'm going to explain to you how I set up this hierarchy. But you will see that there's a pattern to it which can be explained, but I prefer to explain it a little bit later rather than right now. So you'll see the practice, and then you'll get a sense of what actually happens more generally. All right. Successor of addition gives us multiplication, which we call star 1. Taking the successor of that, we've got exponentiation, which is star 2. Taking the successor of that is the triangle operation, which is star 3. And we can keep going in that direction. That's a well-defined sort of sequence of operations defined inductively. This is the successor of the previous. And the limit of that sequence is what we call star n. So we're using star n here rather than star infinity. And then that's just the starting point for a new sequence of successors. So we can take the successor of this one, which is star n plus 1, then the successor of this one, star n plus 2, star n plus 3, and then we have a new sequence here, this one, followed by this one, followed by this one, which has a limit star 2n. And then the successor of that one is star 2n plus 1, and then 2n plus 2, and then 2n plus 3, and then this new sequence also has a limit in similar fashion, which is star 3n. Okay, so these are the limit operations. They are of a different character than these ones. These are successor operations, because they are successors of previous operations. These ones are not successors. They're created from using entire sequence, so we call them limit operations. And then we saw this rather interesting new thing that we could do, which is to look at these limit operations and regard that as the first one, and that's the second one, and that's the third one, and that then generates a new sequence of operations. And of course, then we can take that limit, and we get something which we call star n squared. This is also a limit operation, but it's a limit of limit operations, so it's just one level up. And you can denote that with the two circles here that we're signifying in this particular case. Although we're not going to use circles more generally, just to get you oriented in this session. So this is sort of where we are at currently, and we want to go further. We've seen already this is a humongously big operation, generates numbers which are wildly beyond any of our abilities to imagine. But anyway, we still want to carry on and create higher operations and sort of see how this structure goes. Now, as we write more and more of this hierarchy, we're conscious of wanting to write it as efficiently as possible. So we'll use a slightly different notation here. We'll dispense with 3 dots, and we'll always just usually write 3 things and then go to the limit. So we'll start with addition, and we'll put a comma here representing the fact that this one actually is a successor of this one here. So the comma before this entry alerts us to the fact that this is actually a successor operate. We